my speakers and stuff in my headset.
Okay.
Should be good there.
All right. Okay, good. So we're good to go now, and I'm gonna talk about where we are here. So we are on M8, and today what we're going to talk about is working with raster data. So we spent the last, I guess, 2.5 weeks, because we started out first talking about cursors, and then after we talked about cursors, we spent 2 weeks talking about manipulating vector GIS data, and updating it, inspecting it. And the way that we handle that is by accessing the data row by row in its attribute table. Because really, a geography or a shape is just an attribute. We can think of it as an attribute of a row in a table. So the geography that describes where that feature is in space is one of its attributes, along with any of the other attributes, its ID, or like if it was a road, we can have an attribute that represents the speed or whatnot. And so we can manipulate that. So now we're going to talk about manipulating raster data. And rasters are different. We don't typically have an attribute table. Well, I guess that's not completely true. We often do have an attribute table, and sometimes we don't. Have I talked about this in this class before? In general, like in the ArcGIS world, when does a raster have an attribute table? Does anybody know? You can actually specifically ask ArcGIS to create an attribute table, so I guess that's what you're saying. But automatically, it's created, I think, when there are less than 100 unique values in the raster. So a raster is basically like a picture, a data set that is a bunch of numbers, and those numbers are displayed on screen as using a color map. Yeah.
Is this the one where it's like set in squares? Like
yeah, usually they're shown on the screen as squares. Yep.
Yeah, you can have a number that would be in a square that would be, or something that you need could possibly fit in a square. Like you want to know how many trees are in the area, and then be like that. And that's what we're talking about.
Well, it could be. I mean, the value could represent whatever you want. It could maybe represent the number of trees in a given raster cell.
Yeah.
But it could represent lots of deals. So I'm downloading this WSB DSM that I had on the GitHub page. I'm just going to put that in a new folder called M8, which is this week. So I have it in ctemp M8, and I've got my WSB DSM _TIFW. So I can bring that up in ArcMap or ArcGIS Pro and show what that looks like. This is actually a digital surface model. Let's call this M8. This was a digital surface model that we created, I think, 2.5 years ago for the GHY 315 class. I'm going to add that data to the map. And this is the building that I'm currently in right now. I realize that over half of you are not in this building. But this is a M8. There's the data set. All right. This isn't even the entire data set because I just wanted to get a subset. So here, let's change the base map to see. The base map is actually not very well registered to the actual data set, but it's reasonably registered to it. Okay, so we see here we have the raster that I've just loaded, and behind it we have the world imagery. So I can turn it off and on, and you can kind of see the location, and it's pretty far off, like in terms of its registration. So that's where the building is, the Walker Science building is in the world imagery data set, and that's where the edge of the building is right here. So this tree is really this tree right here. Okay. And that tree is this tree right here. So I've called it a DSM. What do the individual raster cells represent in this data set? The what?
Elevation.
Yes. They represent the elevation, the height above some datum. If I click on the top of this tree here, the pixel value is 48.7. If I click on top of the building, the height is 45.43. So I can infer that, at least at this time, that the tree was an additional 3 meters above the corner of, at least the corner of this building. Now you can see that it goes up here. You guys might not, for those of you that don't come up to our campus very much, this is actually a facade on the front of the building. I don't know if I Google Walker, I wonder if there'll be a picture of it. Science Building, USM. Yeah, here we go. So here's a picture of it. You can see that this gets a little bit taller. It's hard to tell from this picture, but this gets a little bit taller than the rest of the building. You can see that that's the case here. This front facade pokes up above the building in an arched manner. You can see it ramp up. Okay, but we could download a DSM of, or a digital elevation model of the entire campus. Of the entire state of Mississippi, or the all of the United States, or even the entire world. It wouldn't be as fine a resolution, but there are data sets that exist. The closest thing we have to a worldwide data set for digital elevation is the shuttle radar topography mission, which happened in the, I don't know, late 90s, early 2000s. All right. So those are raster data sets, and in fact, the data set behind this data set is also a raster data set. This is a raster data set right here. What are the values in this raster data set? What do those values represent?
Colors?
Yeah. In fact, we're actually looking at, in a way, we're looking at 3 different raster data sets that are grouped into a single data set. Sometimes we call them bands. Who's taking a remote sensing course here? Some of you? Yeah. So there are 3 different raster bands in this raster data set, and we're seeing the combination of displaying the 3 bands in the 3 different in 3 different color guns, red, green, and blue. So right now we're seeing what we would normally see as green is being displayed as green, and what's normally displayed as red is displayed as red. So we call that a natural color image. But we could also display it differently if it weren't for the fact that this data set is fixed. It's being served up by an exterior server, so we can't actually change how it's displayed. We can only display how local data is changed. So we could change the display of this data set and do a color ramp. So there's the Walker Science data displayed using a color ramp instead of just a black and white ramp. All right. So today we're going to talk about manipulating this sort of data in using Python. I think that this USA data is the same as previous before. All right. Now, there are all sorts of raster functions that exist out there. In fact, there's a whole toolbox in ArcGIS specifically devoted to doing raster GIS operations. And that toolbox is called the Spatial Analyst Tools. So Spatial Analyst Tools tools are for dealing with GIS, raster GIS data. One of the ways that we often categorize raster operations is in terms of these 3 or sometimes 4 types of operations. Now we can actually do these on vector data. There's an analogy on vector data, but it often works really well when we do it on raster data. So I'm just going to review these really quick, and then I'll show how we can do these both in the toolbox and then the way that we do them in Python. So the first one I have listed here is the local operation. And a local operation is just where we go into every single cell in the raster and change the value based on some function. Okay, so an operation that takes the value of every raster, feeds it through a function, and puts it into a new output raster that's a function of that cell. Optionally, we could have 2 rasters, but right now we only have 1. We could have raster 1 and raster 2 and feed them through and get raster 3. But the distinction here is that we're only considering 1 location at a time. So for example, if I were to do a operation where I took the values that are currently here, which are in meters, I told you, we could actually verify that. Right-click, properties, and see that the units, the vertical units are meters. Okay. So I could, let's say I wanted to convert this to feet because I'm more familiar with feet. So I could go in and use the times operator, or I could use the map algebra operator, because the map algebra operator is will allow me to do pretty much anything in the spatial analyst toolbox. So there's one called map algebra, the toolbox, map algebra, raster calculator. I can use either one of those. So let's start with times. So that's under math, times. And I could multiply, I could take the WSB underscore DSM raster, and I could multiply that by a value. What value would I need to multiply it by to get feet from meters? It's like 3 something. Meters to feet. There it is, 3.28084. So I'm going to put my input raster or constant value 2 as 3.2804804. So I'm multiplying every value in this data set by that value, and I'm going to output it here. Did you have a question?
Yeah, so it has to be all the numbers past that decimal, or can you do like 3.2?
Well, you could do 3.2, but your number's not going to be as accurate.
Oh, okay.
You can round it, yes, but it's not the same value. So I'm going to put this in this output, but I'm going to call this WSB underscore DSM underscore feet, and then run it. And this creates a layer that is now, it looks almost identical. The only thing is that the range is now different. Okay, it's in feet instead of in meters. So here's feet over here, here's meters over here. Okay. Well, we could do the same thing in Python. I'll start with just doing it in the Python window under Analysis, Python. Okay. Now, before I introduce this, I want to mention that there is, just like there was a whole separate submodule for doing data, for working with for vector data. What model was that called? The submodel. ArcPy. What model did we use to get the search cursor and the update cursor and the insert cursor and all that? It was in a submodule. ArcPy. Anybody remember? It stands for data access. So this is a submodule, the data access module, ArcPy.da. So remember, we had to access all that stuff. Okay. Well, there's a module just for dealing with raster data, and it's called the essay module. Let's see if they have a whole. This is ArcMaps help, so I want to get ArcGIS Pros help. GIS. So we have to import ArcPy.sa, or we have to import it this way. ArcGIS actually recommends doing it this second way, which is a little bit different way than we imported the DA module, which was the data access module. And the DA module, we just used it. We just said ArcPy.da because ArcPy was already imported. So if we import the essay module, we say from ArcPy.sa import star. And what that does is it allows us to use anything in the spatial analyst module without including ArcPy.sa before it. That's what this means. So I'm going to go ahead and copy that line over here and just put it in my Python code. So now I have that. And now I can operate on any raster using actual map algebra syntax. Okay. So here is the syntax for doing addition. I want to do multiplication. So here I just say my output raster is equal to, I have to put it in parentheses, WSB underscore DSM dot TIFF, and then I could say times 3.28084. So now it looks more like not sine. Sorry, I don't even need to do that. I mean, that was the example. I'm just trying to do the same thing that we did earlier, so I just want it to look like that. WSB underscore DSM, to spell everything right, dot TIFF, I need it in quotes, times 3.28084. So what this is going to do is it's going to create an output raster based on this. So it allows me to do it just like a mathematical formula almost. and I'm taking this raster, I'm multiplying everything by 3.28084, and I'm storing it inside of a new variable that I just created called outras. Okay, so if I hit enter there, it says cannot multiply sequence by non-integer type. Oh, this is actually what this means. Raster. I got to turn that into a raster first. So I'm taking raster. If I don't do that, what's happening is I'm trying to multiply a string by 3.28084, and that's not going to work. So I have to tell it that it's a raster. That's a mistake that I made. So we got our raster multiplied by 3.8084. So anytime you have a string that represents the location of a raster, you need to turn it into a raster before you multiply it by anything, or before you do any other operations. Okay. All right, so now I can run this and it should work. So here's my output raster. It did the same thing as this. Okay. However, there is one difference. Where do you think that it stored that out raster on disk? Is there a way to find out where it put it on disk? Yep. And look at where it put it. C users, ArcGIS, app data, local temp, ArcGIS Pro. Like, did I tell it to put it there? Right, it did it automatically. And if the data set was of sufficient size, it actually would have even just left it in memory. It wouldn't have even existed on disk anywhere. And so this one did end up on disk. But if I actually want to take its location and put it somewhere, I need to save it. And so every data set that's a raster data set has a method that you can call called save. Okay, so we can take our raster, our out raster, and say dot, and there's a I think it's capital. Nope, it's lowercase. Save, and then we can specify where we want to save it out onto disk. If you don't do this, ArcGIS will assume that you don't want it. And so as soon as you close down ArcGIS, or even if you're just working in a Python environment, as soon as you close down Python, it will actually delete that data set. So I do have this data set right now, but if I were to close down ArcGIS without saving it, it would go away. So I want outras.save, and I want to save it somewhere. So I'm going to save it. I'll take this path that we have here, and I'm going to call this feed 2 maybe. So I'm saving it in the same location. I'm going to put an R in front of this just in case. That means ignore any special characters. And press enter. And now it took a second, but it saved it to that location. Let's see if it's there. So I'll go over to catalog. I'll go to tool databases. And I'll refresh this database. And there it is right there. So I saved it out onto disk. So when we run a tool using Python, a raster tool using Python, we run it usually as a formula. We set it equal to a new variable, and that variable doesn't exist on disk, or at least we can't depend on where it exists on disk until we save it out. So we always need to make sure that we're doing those things, that we're saving it out if you want to keep it. Dates. All right, so that was running a local function. Okay, a neighborhood function is any function that operates by looking at the. Actually, before I go on to that, a local function is. I said that vector data had a very similar thing that we could do with vector data. With raster data, when we change the individual values of our data, like we just did, we take every value and we multiply it, or we put it through a function, and we get a new data set. We call that a local operation. Well, in vector data, we can do the same thing. We could take every single entity. What's an entity in vector data? Like what's a row? We can take every single row and then choose a column in that row, and we could multiply it or divide it or square it. What do we call that operation in the vector GIS world?
Can you say the question again?
When we take every single entity in a vector data, we take one of its attributes, and we do some mathematical operation on its attribute, and we get a new result. Yeah, well, that's what it's called in Python. Yeah, we're basically calculating out a field value based on another field value, and so what we just did was the same operation really, but we have to do it differently in raster GIS versus vector GIS. But we're taking all of the values that we have and we're multiplying them and getting a new data set. Just like, what if we had all the weather stations in the United States as point files, and all the weather stations were in feet, or sorry, not in feet, in Fahrenheit, and we wanted to get a new field that had Celsius. Well, we take the old field and we multiply everything by that value. So that's how it's similar. All right. So with neighborhood operations, what we're going to do is we're going to operate by going to every single location, looking at its neighbors, doing a function on its neighbors, and assigning that value to the output value, to the output raster data set. So as an example, what we could do is calculate the slope. The slope is looking at all the neighboring operations, and all the neighboring raster cells, and looking at how much change is occurring in that neighborhood. Okay, so the cells nearby are they really different? If they're really different, do we have a high slope or a low slope? Yes. If the neighboring values are really different from each other, then we'll have a high slope assigned to the output layer. If the neighboring values are really similar, we get a low slope value. So slope is a function that's already built into the geoprocessing operations. It's under math. No, trying to close that up. Math. It's under surface. So we got slope right here. We can calculate slope of any of these data sets will work. I'm going to go back to the original, the WSM DSM, and run this guy. And here is the slope. Now this looks kind of crazy, right? The highest slopes are actually the darkest color, which to me is counterintuitive, right? Like these are higher slopes than these areas. So let's change the symbology a little bit. Color scheme. Let's choose one that starts off, or maybe like a blue to red or something. Something that kind of indicates, well, something like that might work. Because here we say the yellows, just a little bit too crazy. There we go. I think that looks a little bit better. So the reds and the yellows, to a smaller extent, are the higher slopes, and the greens are the lower slopes. And so, since this data set is so detailed, we have some pretty high slopes in some areas that we wouldn't really think, but that's just like an artifact of the fact that it's so detailed. So anyway, this is showing that it makes sense that the trees in general have a higher slope than the roof of the Walker Science or the grass area out in front of the Walker Science building. Okay. All right. So how do we do that in Python? Well, similarly, we have to specify a variable to receive the slope function. So we could say slope. Let's call it slope out so we don't confuse ourselves. Slope out is equal to, and we have to use a function, slope. And slope is one of the functions that's available. And since we imported the ArcPy we have that function. So here, if we're running this in ArcGIS, it'll give us some help. If we weren't running in ArcGIS, probably the best way to handle this would be to go under ArcGIS. Well, we could go ArcPy SA, ArcGIS Pro, slope. And if we type that in, we're going to get the help for slope, and we're going to see the syntax for running it outside of ArcGIS. See, we've got the syntax there. Okay. So we need to feed it the data set, the DSM data set. So that's the first one. WSB underscore DSM dot TIF. And then if we hit comma, the second thing that we need is whether or not it's going to, the output is going to be in degree or percent rise. So basically what that's telling us is, I think most of us are familiar with what degrees are, right? Like if I said there's a 3-degree slope, we can all picture that that's a pretty shallow slope. If I said it's a 45-degree slope, that's a pretty extreme slope, right? What's the maximum in degrees that slope can be? What's the maximum in, what's the maximum in, the theoretical maximum in terms of slope? Yeah, it's actually almost 90. If you think about it, it can't quite be 90 because we're calculating slope by looking around at all the neighbors. And so there'll never be, so 90 means that, yeah, well, the theoretical limit would be 89.9999999. It's really, really long. So, yes. Now, percent rise, what percent rise means is we take the rise over the run and we divide that, we multiply that number by 100. So, with percent rise, really it could be all sorts of numbers. It's the rise divided by the run. And so you can get numbers that are over 100%. But what did we do the first time? We did degree. Let's, just for fun, I'm also going to put percent rise and call this 2 and see what how the numbers compare. So it looks like with that one, the highest number we get is 1,000. 1,000% rise. What that means is that the percent, the rise, the run is 1,000 times the rise over the run. So sorry, the rise is 1,000 times bigger than the run. Okay, that's what that means. So percent rise, they measure the same thing. Like you can see that the scale is the same, but we get different units. So it's a matter of preference. So just to keep ours consistent, I'll say degree because that's what we did the first time. And then what are the other variables here? The z factor, the method, and the units. Those are actually all optional. In fact, everything is optional. Even the degree is optional. So I don't have to put that in at all. Okay. So here is just doing the slope on the Walker Science Building in Python. I'll hit enter, and it'll run that. It calls it slope out. But now, where does it put that on disk? Let's look. Oops. Slope out. Oh, interesting. Let's see. That's weird. It's telling me that it put it in the same location as that other data set. C users slope 2, but I didn't tell it to put it there. So how would I put it where I want to put it? In using the save syntax from before. How would I save this slope output to where I wanted to put it?
You have to define it and then give it a C out for your location.
Give it a location. So what would I start typing to get? See this line right here? How would I do a similar line with slope out? Maybe that's too small. What would I type? If I want to save slope out somewhere.
You'd have to put like slope out is equal to.
Not slope out is equal
not
to.
equal to slope out dot save.
Yep.
And then punching your R with the location you want to put it in.
Right. And then put the location I want to put it in. So I'm going to call this GSM, USM, GSS, and I'll just call this slope. So now it's going to save it at that location. It's going to put it there on disk. Press enter, it saves it. If I go to catalog, I can see that I have to hit refresh, but refresh. I can see that it put it right there. And actually in ArcGIS Pro, it's kind of cool that it'll actually update the location of where you put it. So that's kind of nice. Let's see if it did that with the other one. Should have, with the addition one. So there's where we saved it. Yep, it did. It updated where we put it on disk. That's kind of cool. When we use the save command inside of ArcGIS. Okay, now so far, well, okay, one more example, and then I'll talk about that. So far we've talked about neighborhood. Finally, we have zonal and global operations. So zonal and global operations are any operation that operates on the entire data set and returns a value that is either for the entire data set or it's based on a zone, similar to doing overlay. Okay, zonal and global operations. Now, I do teach another class just in raster GIS modeling, and we talk about this in more detail. But I'll show you an example of both of these. So, well, we'll start with zonal. All right, right now I have a data set that represents these areas in near Walker Science. Okay. Actually, let's see what's in this other data set. I think see this USA data.zip. This might be easier. Let me see what's in here real quick. Might be easier to get an example from that data set. So I'm going to take this USA data, copy it to the same location, C, temp, M8, put that in there. And then I'm going to bring a new map. I'm going to insert a new map into my ArcGIS project, because this data is significantly different. I'm going to add some of the data, see what's there first of all. So I put that in C, temp, M8, hit refresh, USA data. So I have average summer temp, average winter temp, and I also have counties. So that'll work. So I've got counties and I've got average summer temp, average summer temperature. Okay. So here's my counties data set, my average summer temperature, and I'm going to add both of those data sets. So if I zoom in here, here are counties, here are the average summer temperatures. I don't really like the way this is displaying, so I'm going to change the symbology and say that, I wonder what, so for some reason everything's pretty low. I'm going to do histogram equalize. No, that didn't work. There we go. Min-max works. Min-max looks pretty good. And then since this is temperature, I might as well do blue to red. Okay. So this is the average summertime temperature map. So the reds and the oranges are warmer than the greens and the blues. Okay. And then here's counties. So let's say that I wanted to take the, I wanted to find out what the average summertime temperature was in every county. Okay. What GIS operation could I do to get that value? Anybody? I'm not talking about Python here. I just want to take all of the counties and find out what the average summertime temperature is in that county. There's probably a few ways to do that. What was your suggestion? A spatial join between the two layers. I don't think that's going to work, but just right off. So the target features would probably be the counties in that case. The join features, we don't have temperature in there as an option. Why don't we have temperature in there as an option? Why isn't that average summertime temperature in there? What's that?
Because it's a raster?
Yeah, it's a raster. So we have a problem because we can't just take the data there and attach it using this tool, because this tool only accepts tables or spatial data, so it won't work. So I know this isn't really a raster GIS class, but there is a tool for doing this. It's called zonal statistics as table. And what this does is it takes any data set, a raster or vector, that has areas that represent zones. So in this case, zones are counties. But it could be a raster data set that represented land cover. Okay. But we can go ahead and choose the counties, and we have to tell what the field is that represents the zones. Raster or vector, we'd have to do this. And so we could go ahead and choose the name of the county. That actually won't be unique, though, because, well, why won't it be unique? Is there more than one Jefferson Davis County in the south? My guess is yes, right? Is there more than one Orange? I grew up in Orange County, California. I know for a fact there's an Orange County, Florida, and an Orange County, North Carolina. I think there's even one in New York. I don't know why.
Do it on the unique ID.
Yeah, so you can do it on the unique ID for that thing. So the FIPS, the county FIPS is going to be a unique ID that will be tied to the county. The value raster is the average summer temperature, and then the output table is the table that we're gonna save the result into. All right, so now we can just export all the statistics, but what we're really interested in is the average temperature for that county. So we'll just look at that though when we finish. So I'll hit run here, and it's going to run along. It's going to take a few minutes. What does it say? Some zones may not have been rasterized. Okay, that's fine. What that's telling us is that there's some. Do we have data in Alaska? No. What it's doing is telling us there's some data that falls outside of the raster. Okay, so let's look at our data. So it's a table, and here we have the mean temperature right here, and obviously this temperature isn't directly in Celsius or Fahrenheit. It's actually in Celsius times 10. So like 218 would be 21.8. Okay. All right, so how do we get this data? How do we display this data on this raster here? This is a raster where we've got every single value represents the temperature, the average summertime temperature of that county. How do we actually make a map of this?
Isn't there a create layer tool with food processing too?
A create layer? I don't know. I don't create geostatistical layer. Anybody else have a solution? We've got a table, and we need to actually attach our table to this geometry.
Can you do it from the attribute table?
From the attribute table.
Like, go to attribute, and then go to one of those and down the corner.
One
I
of
do remember saying how to do it because you could add it to something. I think.
did somebody say something on the coast? It sounded like I might have heard the right answer.
Can you select a road from right clicking it and then create your own layer from that information?
Yeah, that's what I was saying.
All right, so you're saying if I look at the attribute table,
And then right click on row and then go to add to it. Or like,
right click on row, and then what?
go to like okay, so like, so it's like zone code, like at the top, like click on that. And right click. And then go to, so there's a way you can go from there.
Can you go back to the catalog? Go back to right click, go to join relations. Have you already ran this, Dr. Green? You already ran it, right?
Yep. Sorry.
And were you supposed to produce the output? Did it produce the output?
It did. It produced this table
Okay.
right there.
It should be somewhere on there. Could you drag that to it?
It's already added to the table of contents right here.
It's already added.
Yep.
Right click it, go to join relations. No problem. That's join. Somebody join into the.
Yes. So you're very, very close. This is exactly how you do it, except for you would actually join it to the counties layer.
Right.
So we're gonna basically take the counties layer, and we're gonna use the unique ID field that we used before, which is county FIPS, and then join this to the zonal statistics, and we run this, and now we'll have the opportunity to change it to graduated colors and choose the field that we just made, the mean.
And so everybody wasn't completely off.
No, no,
Like everyone in the right direction.
everybody was. Now this this looks a little strange, but there's probably a good reason for it. I mean, those values are correct. I'm not exactly sure why. I mean, why it looks this way, but like for example, why is this so low? Well, the mean value there is 210. I'm not exactly sure why that one's so low. But I mean, I can kind of see how some of these are off. See, if I toggle back and forth between these two, you can see these cooler areas where there's actually mountains. Those end up being cooler.
Can you change instead of 5, change it to 3?
3 what? 5 what? Oh, 3 symbols. Yeah, of course I can do that. Yeah, I'm not saying it's wrong. It's just different than I expected. I mean, we did it, and I don't think that it's wrong. Let's look at just the max. Let's change this back to 5, 6. Huh. The min. There's the coldest summertime temperature in the area. The range. That's interesting.
When you got those natural breaks, can you use something to emphasize natural breaks? Maybe quintile or something.
There's quantile. Yep. So anyway, we did the step there. We took the average summertime temperature and we found the zonal. In other words, everywhere in this county, the maximum temperature in that the maximum summertime temperature in that county was 291, which is 29.1 degrees in this county, whatever the county that is. It'll say what county it is up here. That's Coconino County, Arizona. Wasn't even aware of that county. But, you know, here's Harrison County, Mississippi, and what that means is that the maximum summertime temperature in that polygon was 29.7 Celsius. What is that in Fahrenheit? It's pretty warm, right? We could find out what it is. It's approximately 90. All right, so that is a example of a zonal operation. So how do we do that? Well, this is a different type of operation that actually returns a table rather than a raster. So let's look up and see how we do that in the Spatial Analyst Toolbox. So that one's under Zonal Toolset, and look under Zonal Statistics as table, and you can look down here in the help, and you can see that when you run it, it's still a arcpy.sa tool, just like all the rest of them. However, the output is going to be a ZAS ZAT. So that's going to be, I wonder what that actually is. Because look, here is the output table. That's one of the inputs to the function. Let's try running this in Python. So let's say our output zonal I'll call it ZST, zonal statistics, is equal to, how do we run this tool? We type in zonal statistics as table, there it is. And the first value that needs to be put in is the zone data. So that's the counties. The second data set that needs to be included is the zone field. That was the county FIPS. Then we need to put the average summertime temperature as the value raster. Then we need to specify where it's going to save that file on disk. So here I'm going to feed it. I'm going to feed it the same location we've been saving everything in. So there it is. I'm going to call it something else though. I'll call it ZST2, since this is the second time. And then the rest of those are optional, whether or not we want to feed it no data or all the rest of it. So then we run that, and it created that right there, that ZST2T. It created it. So now that it actually put the output table right there, I wonder what output ZST is. We could ask it, say type of output ZST using the type function. Okay, it's a geoprocessing server result object. Let's just see if it's a raster. Nope, it's not a raster. It doesn't have any methods or anything. So it's in this case, since this particular tool didn't output a raster data set at all, the result is not really as important as this parameter right here, where we decided to save it on disk. Yeah. All right. So that's the zonal and global. Okay. All right. Did she email? I mean, did she email about the tests yet?
Yeah, I ran over and grabbed them.
Okay.
So I have them.
Great. All right. That sounds good. Yeah, we'll do that. Trying to figure out where to put in everything that we're going to do. Okay. I think we'll just keep going for now, and then we'll take our break. Probably about 45 minutes at 1:30, and then we'll have enough time to do the lab. Well, to introduce the lab, and then we'll finish, like I said, by 2:30 the latest, hopefully sometime just before then.
So we would have from 2 until 4, you said?
Yes.
Okay, well, I've just got a text from my boss, and he's gonna come in at 4, but I'll be done before then, obviously. We can
Yes.
start like.
Yeah. I'll try to finish.
Well, man, I'm not trying to rush you or anything.
Right.
Just trying to figure it out.
Sure. Okay. So so far we've only run these tools inside of ArcGIS. So I want to talk about running these tools as a script, because there's usually a few more things that we need to set up. Basically, we need to set up the the ability to, we need to set up the environmental variables. And it's actually more important. The environmental variables that you set up in raster are more important than the environmental variables you set up in vector. Pretty much in the vector data model, 90% of the time, the only environmental variable you're messing with is the workspace. Like, and you're using it for what? Like, why would you set the workspace? What are you helping yourself do when you set the workspace?
Keep all your files in the same place.
Yes. So all your inputs and your outputs, you're referencing them, and you don't have to type the full path to that reference every single time, and it will make sure that you're putting all of your data in the same place, right? So with raster though, you have to think about a few other variables. First, the cell size becomes really important. What happens if you have two raster data sets and you like add them together and they're different cell sizes? What's the default behavior? Do you guys know what happens when you add two raster data sets?
Those are the smallest.
It goes with the largest, actually, which you might not want. In fact, some people would say, why doesn't it just go with the smallest? That's the data set that I really want to mess with. There's a lot of heat coming out of this podium today. So it's often important to set the cell size that you want in your script, because if you don't, you'll get results that you didn't necessarily anticipate or want. This is particularly true when you're converting from vector to raster data, or you're doing an operation that works on vector data but returns raster data. Probably the best example of that is the Euclidean distance tool. What does the Euclidean distance tool do? If I run the Euclidean, what's that?
So it measures on a straight line and not like on a network.
Right, but let's read the help here. ArcGIS Pro. Yeah, it's nice that Google just knows what I mean, right? So I don't have to spell anything right. But yes, thanks for correcting. That was a typo. I know it's a U, but okay. So this is what it does. So the Euclidean distance tool takes a data set, a raster or a vector data set, and returns the distance to the nearest distance to any feature in that data set back to you.
I think that's what I was talking about earlier. Yeah. That's what I thought you had meant earlier when you first started talking.
Oh, okay. Cool.
So it was
The Euclidean distance tool. All right, we're actually going to have to run this later. So let's go ahead and download this Tidexton Parks data, because you're going to have to do that later. And it's got some data sets in here we can show as examples for the Euclidean distance tool. So ctemp lab 3, or sorry, not lab 3, ctemp m8. I'm going to make a third map in here. Oops. I'm going to go ahead and save this. Insert map. And I'm going to add data. Okay. Here's my Tidexton Park data. Right now, I'm just going to add in this data set that represents small-scale agriculture, and also I'm going to add in the extent data set, which is just the one that says watershed, Tidexton watershed. Whoops. Add those two. So here is the extent data set, the watershed data set, and here is the small-scale agriculture data set. Got those two data sets in here. Let's say I want to make a map of that shows the distance to the small scale agriculture data set. And I see already that this is going to be a little bit of a problem. Let me add a different data set really quick. Let's do the urban areas. Okay. You'll see why I did that in a second. Okay. So I've got the urban areas here, and I want to calculate the distance to every single urban area. Okay. So that's the Euclidean distance tool. So if I go to geoprocessing and I type in the Euclidean distance, this is a spatial analyst tool. It's a spatial analyst tool. So if I look at the help for this tool, you'll see that it does have a way to run this using the arcpy.sa command. Right? I could say, okay, I want to take the shapefile and I want to find out how far everything is from that. So here I've got the urban areas, and I don't have any barrier data that I want to input, and I don't want to find a maximum distance. And I could specify my cell size. That's a really weird cell size, so I'm going to pick one that like actually means more. I'm going to go to 100 and then run this. So by default, if you look here, do you see the extent of that data set that I picked? Let's put that up on top of this data set. See the extent of the Euclidean distance output. First of all, what do the values in those cells mean? What do the values in this cell represent? This is a raster data set. Elevation. Not elevation. I ran the Euclidean distance tool.
Distance from urban areas to...
Yes, that's exactly right. Euclidean distance to those urban areas. So these areas right here are the furthest away, and these areas are the closest. And the cells, so when I click this cell, the value of 1,700 means that it's 1,700 meters. That cell is 1,700 meters away from the closest urban area. Now, it's far more likely that I had wanted to specify that the output should be the same in extent as this data set. Like, if this is my study area, I really want to know the value for that entire area, not just this area. Okay. So that's why it's important to specify in the environments what your extent is. So see if I go over to environments and I choose my extent to be the same as the watershed, and I rerun this. Now my data set will be the extent of the entire watershed. So when you do ArcPy environments, what you're doing is you're manually, you're programmatically changing the values in this table, in this environments tab. See that? So the difference between the default and, which I'm going to run it one, see now the default value, which is to have it just be right there, and the using another data set is pretty important. Okay. See that's a big difference. Because see, if I wanted to know what the value was for every area in the watershed, now I have it, whereas I didn't have it before. I can click this right here, and I know that the distance in the watershed, the distance there is 13,764 meters back to the closest urban area.
So would you do like a clip in like based on the watershed so you can just get the watershed?
Yeah, if you just wanted the watershed, in raster, there is a tool called clip raster, and I think it accepts a clip raster. I think it accepts a an output extent, but I don't know. Yeah, use input features. That's what you want. Input raster. So I think this is what you're saying.
Can't you take that and move it all up to the top?
Move what all up to the top?
Shift and bring it up to the top. The Jamaica file, so that the colors will be on top of it.
Yeah.
It looks like it did like.
I just turned off this. Yeah, this is the same. This is the clipped data set that I just ran. I could right click on this and say properties, and no, sorry, symbology, and say import. Now, how do you get it from? There's a way to get it from the other one. Okay, well, these are the same. Like if I click right here and I get the value, it's the same as it is in the other one. They're just symbolized differently. I think I can say, okay, I could go to symbology. So this is classify equal interval 10. Let's see if we can do a similar classify equal interval 10. And then I just have to choose the right. I don't know what the exact, it's not colored the same, but it's the exact same values. The values are the same between each of those data sets. I ran the clip raster tool to answer Ashley's question there. Okay. Now that doesn't mean that there's actually values here. You know that when you clip a raster, it's still a rectangle. Rasters are always rectangles. If I go back to symbology and I tell it that I want to display no data as a certain color, it'll show you that. Like if I went back to classify, or yeah, how come I can't get down any further? Oh yeah, there we go. More. It's not letting me show no data. I don't know where to do that. No data. There we go. No data as like let's just pick black. So the raster is still a rectangle. So when you clip a raster, you're not really making the raster smaller. What you're doing is assigning everything outside of a particular bounding box a no data value, and by default ArcGIS will show that as no color. Okay. But there's still data there. Okay. All right. So we ran this Euclidean distance tool, and we showed how it was important to set the environmental variable to be in this case the extent variable. Okay, so how do you do that in code? Because here, let's just run the same tool again. We're going to do out Euclidean distance for the Euclidean distance for the urban areas. And we're going to say that the maximum distance, we're just going to feed it if you feed it a quote, it'll just be empty. In other words, it'll use a default. Cell size, I did 100. And then that's it. So we run this, and remember when we ran this, we get just that area. It's not the full extent. So it's impossible to set that value anywhere in the input formula. It's part of the environments. So we have to say arcpy dot env dot, what was the name of that? What was the name of that environment? The one that was the extent. Extent is equal to, and here we need to give it an extent. And we could just give it the name of a data set. So I'm going to say, what's the name of that data set? It's the one with the whole watershed. So Ty Dixon underscore watershed. Hopefully I spelled it right. There we go. Now let's try to rerun this. Now you can see that the entire watershed was processed. The entire watershed area was processed. So the extent is the same. Another way to do this that I just thought of, I mean, not another way to do the whole, another way to do what Ashley was asking about before is, let's look at, this might not work, but let's look at that tool, that Euclidean distance, I'm sorry, yeah, Euclidean distance. We go to environments. There is an environment called mask, but I think it has to be a raster. Nope, it doesn't. So there's an environment called mask. So let's see if we set arcpy.env.mask and set that equal to Ty Dixon watershed. Oops, arcpy. And then rerun the Euclidean distance tool. Yep, it looks like we turn off these other layers. Just a second here. What else is still on? Yeah, this one. Nope. There we go. So that's the one that we just outputted. So if you set the mask, you can do it without doing the raster clip second. So that's another reason to think about the environment. So what do the environments do? Well, they also allow us to set the cell size too. So right now I could say arcpy.env.cell size equals 1,000. Now I get bigger cell size. And now I can run this tool without specifying the cell size, and it will use the environment cell size. And I'll show you if we, well, it's obvious even from here, right? The cell size is larger in the new data set that I just ran.
Is it 1,000 meters or 1,000?
It's always in the same units as your data set. So our data set's in meters, and so you can find that out in if you right click and look at the it's actually under spatial reference. This is the vertical units, but the The regular units or linear units right here, meters. Okay. So that is that's environments. So there's a few more environments that are really, really important for raster data. Okay, so I think we've covered most of the ones that are pretty important. Extent is really important. Cell size is really important. The default cell size is the maximum of inputs. So if you want it to be a certain cell size, you could actually specify that the data set, that the cell size. In other words, you can go arcpy.env.cell size, and you could specify a data set instead of specifying an actual number. So we could specify outras as the cell size. Anybody remember what the cell size was on outras? It was like really small because it was the raster of Walker Science Building. So now we've set the cell size to be the same as the Walker Science Building data set. So if we try to run this again, it might even crash because the cell size is so tiny. I'm going to try to run it. See how, looks like it ran just fine, but the cell size is a lot smaller again, okay, than it was when we ran it with 1,000. Okay. So you can specify the cell size to be a data set, or you can specify it to be a number, just like you can specify it here to be a number, or you could specify it to be any of these: minimum inputs, maximum inputs, same as any layer. So you've got all those options. All right. So extent, cell size are really important. Those are the ones that we covered. Mask is pretty important. If you want to limit the area that gets processed and not have to clip it out later, you can use mask. Now remember, even with mask, there's still values over here. See how it says no data? There's still no data values out here. Now if I click over here, there's no datas out there because it's always a square, or not a square, a rectangle. So if I click out here, there's nothing. But if I click in here, no data. All right. So the last one that I want to talk about that's really important is called the snap raster. I think that's the last one. Let me look at my notes real quick. This one. Go back here. Just make sure I talked about. Well, I just said cell size. Okay. Okay. So cell size. I didn't mention any of them, but the last one I want to talk about is snap raster. What does snap raster sound like? Snap raster will make sure that the corner of your data set is the same corner as another data set. That's what snap raster will do. So if I have the out Euclidean distance, see how this corner of the data set is up there? What it's going to do is make sure that the corner of this data set is also a let's look at the 1,000 one. Where's the, I don't know where I put it. So this one? Yeah. So it's going to put, right now, the corner of this cell is different than the corner of this cell. See how they're different? Like the corners don't line up. They're not the same. But if I say I want my snap raster, I can set the snap raster here. I'm going to go arcpy. I'm going to change the cell size back to 1,000, but I'm going to change the snap raster to be, they're all called the same thing. Let me see what this one's actually called on disk. I'm getting the full path of this data set. So the snap raster, oh, I forgot to put an equal sign. Snap raster is going to be equal to that data set. And now I'm going to try to rerun the Euclidean distance. Yeah, I was afraid of that. So snap raster doesn't usually work unless you also set the cell size to be the same cell size. See how it still didn't line up the corner of that to a cell. So it will work though if we set everything to be the same. So now I'll do cell size, and I'll set the cell size equal to that same data set, and then rerun it. And it's going to be smaller, but they are going to line up. It's hard to tell that they line up. Well, you can tell that they line up, see, because this cell right here is the same size as all the other cells. So they're lining up the same between the two data sets. I got to turn off this one. So this one lines up in terms of the location of, well, you can see the edge of this raster and the edge of that raster are the same. So they line up perfectly. In other words, they're not slightly mismatched. That's what snap raster does. So if you ever convert two different vector data sets to raster and the cells don't line up and you really want them to, the environment variable called snap raster is the environment variable that you want to mess with. Okay. So that way the rasters will line up. Okay. All right. So yeah, it's about 1:15. Let's go ahead and take our break right now, our 1:15 break, and then I'll talk about the lab. And as part of talking about the lab, I'll cover these other things I want to talk about, and then yeah, this will be next. That's really next week. Okay, talk about that next week. So let's come back here at 2:30, and I'm going to go ahead and stop this, and then we'll do the test. We'll have about 45 minutes to do the lab, and then we can start the test. So you're welcome to take a break before you start the test, or you can go right into it, either way.